Okay, let's go ahead and get started. Thank you everybody for attending and coming on to the seminar. So today we have a great seminar lined up for you guys by Raghav Bansal from Cozy Finance on Agent Buttercup. Agent Buttercup is a flexible Rust-based framework for running computationally intensive ABMs or agent-based models in an EVM environment. Raghav's going to showcase how Agent Buttercup can enable us to understand what drives the outcomes for complex systems. But yeah, without further ado, Raghav, I'll go over and hand it over to you.
Yeah. Hey, everyone. Thanks for having me here today. I'm Raghav. I work on R&D at Cozy Finance. We're a DeFi protocol for protection markets. And as mentioned, I'm going to be talking about an open source tool we put together to run agent-based models called Agent Buttercup. So what is it? It's a flexible Rust-based framework for running computationally intensive ABMs in an EVM environment. I think most people in DeFi are somewhat familiar with ABMs, but I just wanted to start with a very brief overview and explain why we think they're a powerful tool for sort of speeding up the protocol design process. Um, so, uh, ABMs are generally a simulation technique, which allows you to understand sort of what is driving outcomes in a complex system. The key idea is that you have agents who are continually interacting with some environment. So this visual here is somewhat insightful. Your agents basically have some objectives. They percept the environment. They figure out what actions they need to take to reach their objectives, and then they act on that environment. So it's ABMs are actually used pretty across the board in a bunch of different industries, self-driving cars, tradings, epidemiology. So actually when like COVID-19 was breaking out, ABMs are a popular way to model a spread. Your agents are effectively counties or even individuals. You had data sort of on their incidence rate, demographics of those counties. Your agent sort of contracted COVID-19 with some probability and potentially put like surrounding agents and counties at risk. That sort of gave like a quantitative way for people to figure out if different interventions like mass or lockdowns could sort of help contain overall spread. And so in general, they're most powerful when it's difficult to reason about like the macro level behavior of a full system because it's pretty complex and the actions different agents are taking sort of depends on the actions and outcomes of different other agents. But it is really easy to reason about sort of the micro level behavior of subsystems or specific agents. So ABMs in DeFi, they basically give protocols a way to run a computational experiment and generate simulated data. You can then use that simulated data to answer all sorts of questions. So you can evaluate new mechanisms, how they may affect sort of market outcomes of your protocol. You can optimize risk settings, model parameters. And if you're sort of worried about economic corner cases in your protocol, you can stress test those scenarios as well. So when you use ABMs, you're obviously generating simulated data. So for the results to be meaningful, you have to make sure you're modeling your agents correctly and that your environment sort of approximately matches reality. So like what would be the alternative if you wanted to make much less assumptions about your agents or the environment? So if you think about like big tech, a lot of the time they'll run A/B tests to basically figure out, all right, does this new feature or algorithm sort of affect impressions? And there you can make a lot less sort of assumptions on how people will interact with your feature because you can sort of collect real data. It's not really feasible in DeFi because for a few reasons, it would just take way too long to collect sufficient samples. The second one is like the major constraint, which is that you can't really deploy contracts every single week or every single month. You can only test things like A/B test things that on your currently deployed set of contracts. And then finally, to run an A/B test, you need like randomization. It needs to be non-manipulable randomization. And we know that's sometimes difficult to get on chain. And so for Cozy, our real goal with ABMs was to enable iterative protocol design. The idea is basically we have a code base. It consists of our protocol smart contracts, a set of agent models, and a simulation environment. Agent Buttercup is sort of the wrapper on top of all of that. And now when we're working on a new mechanism, like if you're working on new cost models, if you're AMM now working on like solving LBR with some dynamic fee mechanism, you can effectively iterate a lot quicker. So you can implement your new mechanisms in your Solidity smart contracts, run ABMs, get results, get sort of quantitative data on how this might affect the economic behavior of a protocol, figure out what you can improve, edit your mechanism, and sort of iterate a lot faster. So I'm going to talk a bit about the code and the architecture. But before that, I sort of want to lay out some of the design goals we had in mind when we were setting up Agent Buttercup. The first was we wanted to be sort of laser focused on ABMs. So really enable that iterative process I just described in the cleanest way possible, sometimes trading off like full flexibility for simplicity and making it easy to sort of get these ABMs up and running. So you'll see how that comes into play as I dive deeper later. Second thing is we obviously wanted this to be fast and scalable. That's why we chose Rust and also wanted to avoid any networking overhead, IO, port-to-port communication from JSON RPC calls or the like. It sort of excluded doing anything directly on top of a local node implementation like Anvil. So that's why in our SIM environment, we're going to be directly working with our EVM instance. Third, we wanted to match our SIM environment as closely as possible to deployed contracts. So we're going to generate Rust bindings. We're going to use all the nice tooling in Foundry, in Ethers RS, use Forge Bind to sort of generate Rust bindings. So you can sort of just edit your contracts. You know that you don't have to re-implement your contracts in, for example, Python or another language. You're directly working with the contracts that you're eventually going to deploy on chain. And the final thing is there's obviously lots of nice tooling and Rust-based EVM infrastructure being built out. And so we wanted to make sure that we were in a place where we could be compatible with that and integrate with those new code bases. I'll go through the core components of Agent Buttercup to sort of help you understand how it works. And so there's 5 key components. There's going to be a thing called state, agents, time policy, and summary generator. And the last thing is going to be the manager that's sort of going to own all those 4 things above and going to coordinate them and actually kick off the SIM. Okay, so what's state? The state is basically an object. It's going to keep track of 2 things. One, it's going to keep track of EVM state inside of our EVM instance. And 2, it's going to keep track of any non-EVM state inside the separate thing that we call world. So world is basically a way for you to track any non-blockchain data that you think is relevant or that you can't pull from the REVM. So if you're sort of, for example, writing an agent that's an arbitrageur, trading between an AMM and a sex price, you can store sort of current sex prices there. If you're modeling some sort of liquidator, they sort of care about volume on some other venue or off-chain venue so they can calculate slippage. You can sort of store that data there and model that data there. And actually in Cozy, we sort of use world in a more flexible way also. So we have some summary statistics on our markets, like APYs and utilizations and so forth, that you actually could directly get from the REVM instance, but it would require 6 or 7 EVM calls in order to calculate those statistics. So we just simplified things a lot and just had essentially an agent that we call the sort of our market analyzer, sort of calculates those and just stores them in world so all the other agents can read them easily without having to do the calculation themselves. And then, so the simulation is basically going to give you a way to execute EVM transactions through the REVM instance. It's also going to give you a way to execute updates against world. And it also has some tooling to easily interface with REVM to deploy new contracts, read account info, simulate transactions. All right, so the next key thing is obviously agents. So agents are going to be a trade object. They're going to basically be pretty simple. They have to implement 3 functions. It's going to be activation step, and resolve step. So I'll walk through these. So the activation step is basically called once when the agent is first created. And here the agent is basically free to update freely update state as necessary for any setup purposes. So you'll see here that they get like a mutable reference to state. So they can basically do whatever they want. They can deploy new contracts. They can query their balance, do whatever they want here. And all of this is going to happen before sort of the core simulation loop kicks off. This is just for setup purposes and is only called once. Most of the logic that you care about is probably going to be in step. So this is going to be called on each step of the simulation. This is sort of where the agents are going to potentially read state, figure out what actions they want to take, and then send those actions to get executed against state. So you see here, like unlike the activation step, they're not going to get a mutable reference to state. Here, they're only allowed to read it. They can't update it or inside the step function itself. The way you sort of signal the actions you want to take is by using this message passing channel, which is called a channel right here. So just as like a quick example here, if, for example, you have an agent, they have some ERC20 contract, they want to approve some address, you can use sort of your Rust bindings for that token contract, call approve, and then sort of tell the channel you want to execute that EVM transaction. Similarly, if, for example, you have a world implementation, you have someone who's like updating sex prices, they can send this sort of sex price update with a timestamp and a price and ask the simulation sort of update world with that new data. Okay, so then the final thing is going to be resolve step. So after all agents have sent in sort of the updates they want to execute against state, whether that be via against the EVM or against the world, now agents need to figure out basically like, all right, what happened with my update? For example, if it was an EVM transaction, did it revert? Was it successful? Or like, what was the output of that function? What was the sort of like the output of that call? And so you can sort of do that in the resolve step, which is going to be called after each step call. And basically, it's going to allow the agent to sort of retrieve the outcomes of their actions, again, via this message passing channel. So here, for like the last two transactions we sent, you can sort of figure out, did your token approval pass? Set calling receive EVM transaction output. I don't think you'd actually need any update for like a sex price update, but potentially you're allowed to like receive output from world updates as well. All right, so the next thing is there's this time policy. So for when we were designing this, it was really important for our protocol that we'd be able to like fast forward time in the EVM, in the REVM. And so the time policy trait basically defines how the EVM block timestamps and numbers are going to progress forward in the simulation steps. So again, this is really simple. You just sort of define on each step how much your block number or block timestamp move forward. There's like a default implementation in the code base that just moves forward a fixed amount of time per step. So like typically how you think about Ethereum blocks moving forward 12 seconds. But it's obviously customizable, which is sort of nice because if, for example, you have a low frequency protocol, you don't really care that agents take steps every 12 seconds. You maybe only care that agents take steps every hour or every day. You can implement that in your time policy and sort of reduce the sort of computational burden on the sim. The next thing is the summary generators. So on each step, we're going to want to potentially collect some data about the economics of our protocol, what happened, so forth. And so summary generators are just a general way to define what statistics you want to sort of read or compute from EVM and world state. And they're basically can generate some JSON data that gets written to an output file so that you can analyze that as needed after the simulation is run. All right, cool. So then how does this all come together? Everything sort of comes together with the manager object. It's going to sort of own the time policy, the agents, the state, the summarizers, and it's going to be responsible for kicking off the sim. So it basically has this function, run sim, and it effectively runs a loop where these steps happen. The agents are sort of processed in parallel across multiple threads. send updates via their step methods. The manager collects those updates, executes them against the state. Results are sent back to the agents. Agents can then process the results via results step. The summary generators will run and statistics are written to an output file. And then finally, it sort of asks the time policy how much it should move forward, the EVM time and block number for the next step. So I won't go through this in detail, but this is sort of like a diagram of how this works. So this is like, you can see here, everything here is owned by the manager. The key thing here is that the core primitive is this idea of the simulation loop, where the manager calls steps on the agents send back transactions, it executes transactions, it lets agents resolve their steps, it runs the summarizer, calls the time policy, and basically loops until the time policy is done. All right, so that was the architecture. I quickly want to walk through sort of what the workflow would be if you wanted to get Agent Buttercup up and running for your protocol. So the first thing is you want to generate Rust bindings for your contracts. Then Ethers RS and Foundry have tools to do this. You can just use forge bind basically. And we have some like scripts and so forth in our code base to help you do that if needed. Second thing is you're going to want to define your rolled object. This is like a trade object, so you can define your own concrete implementation to sort of track any non-EVM state that you think is important, as well as like all the sort of actions agents can take to sort of update and mutate that rolled object. You pick a time policy, you define your summary generated implementation. So what are the things you want to collect data for? You define your agents. And then once you get to actually running the simulation, you're basically going to have a very simple process of calling activation step on each agent, and then calling that run sim method, which will kick off the core simulation loop. And then it's going to generate a bunch of output data that you can analyze. So I wanted to give sort of concrete example of how we're using this at Cozy Finance and why they're useful. So we have essentially Agent Buttercup setup. And I guess for those who aren't familiar with Cozy Finance, we're sort of a protection protocol. So we have people who sort of buy and sell protection on some binary triggers like acts or DPEG events. So we defined a set of agent types that we think are important. These are like protection buyers, suppliers. We have this thing called a set, which is like a wrapper around several protection markets. So we have set admins, we have trigger admins who are people basically responsible for saying, all right, did this ACK or DPEG event happen? And if so, like trigger the event in the Cozy smart contracts. And we sort of have arbitrageurs who sort of trade around their view on the fair price of protection. We have some like risk settings, which are like the probabilities and correlations of triggers. And we have set settings, we sort of define the leverage and number of markets in a Cozy set. And so like all of these parameters you can see here, I just took a screenshot of, or sort of stored in this config YAML file that we have. So why is this really nice for us? This is really nice because we basically have a benchmark suite of ABMs that we can run on any new mechanism that we want to try out or test. And essentially we can like vary these parameters in this file and generate a bunch of simulation results and get a full picture of the protocol's economic behavior and sort of really enable that fast iterative protocol design process I talked about earlier. So even more concretely, this is just like an example of a specific analysis that we run. So we have sort of cost models in our protocol that define what is the cost of protection. And we wanted to sort of compare static jump rate models. This is similar to what sort of lending protocols use to define interest rates, to something a little bit more complex, something like a PID controller called dynamic level cost models. And we're basically able to use Agent Buttercup to generate simulation results under different settings. And it helped us sort of like quantitatively confirm what we thought, which is that like dynamic cost models can be more effective at like driving the market to optimal utilization and APYs. So you can see here, we basically have some like Python code, which just generates all these plots and summary tables for each sim run. And then, so I guess the last thing I wanted to give you a sense of is basically the speed of Agent Buttercup. So usually for us and our setup, we can run a useful sim in under 1 second. But obviously, if you have a very large number of agents or steps, it can take longer. So you can see here for like we typically are using between like 10 and 500 agents in our sims. And those run between like half a second to a second, here 2 seconds. And it's processing quite a bit of EVM transactions. So here's around 30,000 EVM calls, 3,000 EVM executes, around 300 world updates. Obviously, in like if you're running like a very large sim with a very large number of agents, here it took like 17 and a half seconds, but it's also processing almost 500,000 EVM transactions. So we think for most practical purposes, this is pretty fast and hopefully helpful for protocols who want to run sims on sort of regular basis as they're iterating. So there's lots of improvements we can make to this. We currently don't have it. We can't really easily fork Ethereum mainnet state, for example, onto our EVM before running the ABMs. Always interested in thinking about if we can speed things up more. It would be nice to have better integrations, for example, with Foundry. For example, we have Foundry scripts which deploy our protocol. It'd be nice to just directly use that Foundry script in Agent Buttercup rather than having to like write the deployment logic again in an agent or in the setup of the sim. And so, yeah, definitely reach out if you're interested in contributing. This is sort of like the repo and any contact info. And yeah, that's all I have. So happy to answer questions.
Great. Yeah, thank you so much. If anybody has any questions or comments, please feel free to leave it in the chat, or feel free to unmute if you're not too shy and go ahead and ask Raghav directly. But yeah, we'll give it a few minutes if anybody has anything they want to ask.
Sounds good.
And I think I just wanted to ask this. I know I asked you before we started, but just so everybody has context on. But if you could kind of give a quick overview of like, where did Buttercup come from and kind of like, how it came to be.
Yeah, so obviously Cozy's sort of mascot is the Cozy Sloth. And Buttercup is actually like a somewhat famous sloth. It's like the oldest sloth, but unfortunately passed away, I think, a few years ago in 2019. But that's sort of behind the branding here.
Cool. Well, I think there doesn't seem to be any questions left. But I think, again, fantastic presentation. It was really clear and concise. So I'm glad that, folks trickled in and it was easy to understand. But yeah, again, Raghav, thank you so much for your time. Really enjoyed it. And yeah, for everybody's context, I think we might have one question trickling. I think Slowfi is typing. And DefSec. Oh, just thank yous. Well,
Okay.
likewise, guys. Thank you everybody for attending, and yeah, hope to see everybody soon. This will be posted on YouTube, and the slides will be provided as well.
Awesome. Thank you for having me.
Yep, absolutely. Take care.